So just get the week 2 one that I sent you.
Yeah.
Purity table.
This one.
Yeah. Okay. So this is the stuff that we started learning at the start, but I think you'll be able to understand it better now that we've done like a little bit of other stuff about it, right?
Yeah.
So just straight down, let's just go down the back. Do you want to tell me what an element is?
Element's like an atom.
An element is made of atoms, yeah. But like that's not what it is. So all of these things right here are elements, and by definition, an element is something which is already in its purest form. It can't be broken down anymore, right?
Yeah.
And so, like for example, zinc is just zinc. You can't break it down to anything. Is water an element?
No.
No, because it's H2O. I can break it down into the H's and the O's, but zinc is just zinc on its own. There's nothing to break it down into, yeah? So an element is the most purest form, and it can't be broken down into anything, yeah? What about an isotope?
Wait. Something that can't be broken down.
No. So we just explained it in the last.
Yeah, I know.
In the last thing.
Is it when there's two different like chemicals, like two different numbers of the chemical?
Close. So it's when there's two atoms that are the same. So they're both carbon, or they're both nitrogen, or they're both hydrogen, but they have a different mass because one of them has more
atomic number.
No, I don't know. One of them has more or something.
Mass.
Yeah, but why? Because it has more. Neutrons, right? So one of them has more neutrons than the other. So for example, I can have two hydrogen atoms, but they won't be the same mass all the time because one of them could be an isotope that has more hydrogen atoms. So that's what isotopes are. They just are versions that have more atoms than the other version. Okay?
Yeah.
Make sense? Okay. All right. What about an ion?
In the middle.
What's a neutron again?
Negative charge.
Are you sure?
Oh, neutron. Is neutron the medium charge?
So neutron has no charge. It's neutral. That's where the word neutron comes from. It comes from the word neutral. Does that make sense?
Oh, yeah.
So a neutron doesn't actually have any charge. Yeah? Okay. What about an electron?
Negative charge.
Negative charge. Okay. And what's in the nucleus?
Neutrons? Sorry, electrons.
Okay. It's the protons and the neutrons that are in the nucleus. The electrons are in the shells. So you can think about it like this. There's a middle of the atom, that's the nucleus. Surrounding it is the electrons. So the nucleus is in the middle, it has the protons and the neutrons. Surrounding it is the electrons. Does that make sense?
Yeah.
Okay. Really quickly, just go to page 3. All right, and so those terms right there. So starting with ionization energy, electronegativity, metallic nature, atomic radius, and then oxidizing strength and reducing strength. I'll explain them to you, and then I'll give you some time to revise them as well. So we're going to start off with ionization energy. Ionization energy is the energy needed to remove one of the electrons. So remember, Nucleus in the middle, electrons surrounding it. If I want to take one of those electrons and remove it, that's my ionization energy. So ionization energy is a measure of how much energy I need to remove one of those electrons from an atom. Okay?
Neutrons, right? Or electrons.
Electrons. So electrons are the one in the shells.
Yeah.
Yeah. So ionization energy is the amount of energy I need to remove one of those electrons from the shell. Electronegativity, on the other hand, is how strongly attracted electrons are to an atom. So let's say that right now I put an atom here, electrons will move towards it because they're attracted to the atoms. But different atoms will attract the electrons differently. Some will really attract it, some will only attract it a little bit, okay? So electronegativity is a measure of how strongly attracted they are, yeah? So can you just say that for me? What's ionization energy and
Yes.
electronegativity? What's the difference between the two?
Ionization energy is how much energy you need to remove an electron from the atom.
Mhm.
What's the other one? Sorry.
Electronegativity?
Electronegativity is how much negative charge it has.
No. So electronegativity is how strongly attracted electrons are to the atom. So you can think about it like
That's the
this.
opposite.
Ionization energy, you're taking it away. Electronegativity, you're bringing it closer. But they're both measures of strength. So what's electronegativity?
Electronegativity is how much energy you have to, like, how much energy you have to pull it to.
Close. It's how strongly attracted an electron is to an atom. So how strongly attracted is that electron to the atom? So you think about it like this, right? Let's say that right now I had an atom over here, right? So I just have an atom over here, and I have an electron that's just floating around. That electron is going to be pulled towards the atom. Sometimes it's going to be pulled really, really quickly. Other times it's going to be pulled really, really slowly. And so electronegativity is a measure of how strongly attracted it is. If it's really attracted, it will move quickly. If it's only a little bit attracted, it will move very, very slowly. Yeah? So electronegativity, what is it?
How much energy? How strong the amount of energy has to get into the atom.
All right, close enough. Atomic radius. What do you think this means? Break the word down. Atomic radius.
Half of the atom.
Right? So the radius of the atom. So in other words, it's a measure of the size of the atom, right?
Yeah.
Okay. That's the only the four that I want you to worry about. So can you just revise those four for me? So ionization energy, electronegativity, metallic in nature, and atomic radius. Oh, we didn't do metallic nature. Metallic nature is the how likely is an atom to lose an electron? Yeah, that's what it is. So amount of energy needed to remove an electron, how strongly an atom attracts electrons, and how likely an atom is to lose electrons. So they're all very similar.
Wait, what's this one again?
Metallic nature, how likely an atom is to lose electrons.
To lose
Electrons.
Okay.
So if it's very likely, it has a strong metallic nature. If it's not really likely, it doesn't want to lose electrons, it's got a low metallic nature. So I just give you a few more minutes to revise those. Those four, sorry.
Oh, there were two more.
Yeah, well, we won't do those two.
Okay.
We'll leave those for later.
So what did you say was the third one again?
Metallic nature.
Yeah.
How likely an atom is to lose electrons. So if it's losing electrons a lot, then it's
So how likely? Sorry, I keep.
how likely an atom is to lose electrons.
Okay. Yeah, I think I'm.
Right. So ionization energy.
Ionization energy is the amount of energy it loses from the amount of energy it loses from the atom.
No. What about electronegativity?
How strong the energy is to attract the atom.
Right. What about metallic nature?
How likely the atom is to lose electron.
All right. Metallic nature is the only one you got wrong. You got right. So yes,
Oh, there's another one.
Yeah, but don't worry about the other one because I know you know that one. So metallic nature, yes, you got that right. How likely it is to lose an electron. The other two, you didn't get them right. So electronegativity is how strongly an atom attracts electrons.
Wasn't that kind of what I said?
You said how strongly an atom takes energy. So like you're on the right track, but you need to say the specific words. How strongly an atom attracts electrons. How strongly an atom attracts electrons. Just 6 words. Electronegativity is how strongly an atom attracts electrons. Ionization energy is, again, how much energy it takes to remove an electron, right? The amount of energy to remove an electron versus how strongly an atom attracts an electron, right? So I'll ask you again. So just like look through it. Electronegativity versus ionization energy.
I could say the amount of energy to remove an electron from an atom.
Okay, that's ionization energy. What about electronegativity?
How much energy it has to attract the electron to an atom.
Okay, that's better. All right, cool. All right. So what I'm going to do for pretty much the rest of this class is just explain some things to you. And the first thing that I'm going to explain to you is these numbers at the top, right? So you see on the periodic table how there's those numbers, like if you start from hydrogen and go that way, there's 1, 2, 3, 4, 5, 6, 7, 8. You see that?
Yeah, I do.
Those numbers aren't made up numbers, they're real. What those numbers mean is that's the number of protons and electrons an atom has. So for example, carbon is number 6. So how many protons does it have?
Wait, what?
So carbon is number 6, right? And so that number 6 tells me that there's 6 protons and then there's 6 electrons. So it tells me the number of positive things and the number of negative things. So for example, how many protons and electrons does beryllium have?
4.
Okay, cool. Now, what you can see is as I go from left to right, those numbers are increasing, correct?
Yeah, the atomic number.
Yes, good. The atomic number is increasing. And so that means that the number of protons is also
increasing.
Now, where are the protons in the atom?
In the nucleus?
In the nucleus, so in the center, right?
Yeah.
And what's the charge of protons?
For each one?
What's the charge of a proton? Yeah.
Plus.
Plus, right? So it's positive. And so as you go from left to right, the number of protons is increasing. And as you said, the protons are in the center. And if the protons are positive, that means that there's more and more positive charge in the center of the atom. Is that correct?
Yeah.
So that center of the atom gets more and more positive, correct? And so, do you think that the electrons on the shells are more attracted to the center or less attracted to the center?
More attracted.
More attracted to the center. So as you go from left to right, what I can say is that my core charge or my charge in the center goes up. And due to that, my electrons are more attracted to the center. Does that make sense?
Yeah.
And so you can think about it like, let's say that you had, like 100 people all in a circle, right?
Yeah.
And then in the middle of the circle, you put $100. some people move towards it, but imagine you put $1 million, then everyone would rush towards it, right? And that circle would get really small. And so as you move from left to right, do you think the atomic radius is getting bigger or smaller
Bigger. Wait,
as you go from left to right?
left to right. Oh, smaller.
Smaller. Why?
Because it's
You're right. Yeah, but why?
because the more there are, like the less space. Kind of thing.
Well, it's about what I just said. So it's like as you go from left to right, there's more protons, and that means that the charge in the middle is greater. And so that means that the electrons are more attracted to the center and then they move in.
Yeah.
Yeah?
So there's more space. Basically.
No, there's less space.
Yeah, I know. Oh yeah, sorry, less space.
So, but you have to explain it like that. So you need to say that the core charge goes up because there's more protons, and that means that the electrons are attracted more towards the center. All right? Does that make sense?
Yeah.
Okay. Now, there's another thing. So you've just gone from left to right. We also need to know how to go up and down. And so let's say that I look at hydrogen versus lithium versus sodium versus potassium, right? They're all in the same group. Now, the rule is that like this one here will have 1 electron shell. This one will have 2 electron shells, 3 electron shells, 4, 5, 6. Same thing. 2, 3, 4, 5, 6. 3, 4, 5, 6. 3, 4, 5, 6. 3, 4, 5, 6. So it tells us the number of electron shells that something has, yeah?
Yeah.
And so do you think the atomic radius is getting bigger or smaller as we go down?
Smaller.
Why is it getting smaller? If we're having more electron shells. So you can think about it, like imagine 1 electron shell, and then you have another one, and then another one, another one.
Oh,
You're adding more shells, right?
Yeah.
So it's like an onion. Imagine if an onion has more layers. Is it going to get bigger?
Bigger, yeah.
Yeah, exactly. And so 1 shell, it's small. 2 shell, it's getting bigger and bigger and bigger and bigger and bigger and bigger. So it's like you're having more layers of an onion, right?
Yeah.
And so the more shells I add, the larger that atom gets. Okay?
Yeah.
So explain to me what happens to the atomic radius when I go from left to right and why.
It gets bigger.
You sure? From left to right. From this side to that side.
Smaller because more space.
So what was the explanation that I gave? Because that's not like enough of an explanation. So what did I say happens when you go from left to right?
It gets smaller.
Yep, but why? Okay, so I said again, as you go from left to right, the number of protons increases, and you can see that because the atomic number is increasing. And this means that the core gets more positively charged. If the core gets more positively charged, then the electrons are going to be more attracted to it. And so that means that the electrons will now move closer inside, and so the atom gets smaller. All right. So again, why is it that when I go from left to right, the atomic radius or the size of the atom gets smaller?
Because the protons are higher, and so when we will get higher, and so the core of the nucleus, like the electrons, will get bigger.
What's getting bigger? The electrons are getting bigger.
It's electron charges.
All right. So I'll explain it again. Just listen carefully. So as you go from left to right, more protons. Look, 19 protons, 20 protons, 21, 22. The number of protons increases. Because protons are positive and they're found in the middle, now that middle gets more and more charged. So it gets more positive. And that means that the electrons are more attracted to it, and so the atom gets smaller. So the core gets more positive, and then the electrons are attracted to it more. It's like you're putting more money in the middle of a room, and then more people are moving towards it, right? So the core gets more positive, and then the electrons get closer towards it. And that's why the atom shrinks. It's like, imagine I put $10 in the middle versus $100 in the middle, more people will move closer towards it. Yeah? All right. So can you try to explain that? Because this is super, super important.
The protons increases, and since there's a positive charge, the core will be positive charged, and electrons will increase as well. The electron charges will increase.
The electron charges, This has nothing to do with electron charges. Nothing happens to the electrons. It's just that the electrons are more attracted to the middle.
Oh.
Has nothing to do with electron charges or electron charge increasing. Electron charge can't increase. It's just that they're attracted more. So that's like saying, you know, back to my room analogy, that's like saying the number of people is increasing or how happy the people are increasing. That's not what's happening. They're just being more attracted to the money because there's now more money. That's what's happening, right?
Yeah.
So it's like if you had like 2 really strong magnets versus 2 weak magnets, there's more attraction. The magnets aren't behaving differently. There's just more attraction. Yeah? Okay, what about down the group? What's happening down the group to atomic radius?
It increases.
Why?
Overnight, so it gets smaller.
No, it gets bigger.
To do with the shells, right?
Mm-hmm. What about the shells?
The shells increase.
All right, how many shells does hydrogen have?
1.
What about lithium?
3.
No. So remember,
1.
1, 2, 3, 4, 5, 6, 7. That's how it works. It's not to do with a number. So it's 1, 2, 3, 4, 5, 6, 7. So how many shells does lithium have?
1.
No. Hydrogen has 1.
Oh, sorry. 2.
What about sodium?
3.
Potassium?
4.
All right, what about iron?
8.
Where'd you get 8 from?
I counted from left to right.
Right, remember, we're going downwards though. So everything here has 1. Here, 2, 3, 4, 5.
Oh, yeah.
So everything here would have 2. Everything here would have 3. Everything here would have 4.
4. Yeah.
So iron only has 4. All right, what about bromine?
4.
Chlorine?
3.
Iodine?
5.
Okay. Now let's think about something. Think about electronegativity. What's electronegativity again?
How strong the energy is, like from electron to atom.
Okay. Now let's think if the core or the middle of the atom gets more and more charged. Do you think electronegativity is going to get better or get higher or lower?
So positive.
Yeah, if the positive charge gets higher in the center, are electrons going to be more or less attracted?
More.
Okay, so as you go from left to right, is electronegativity increasing or decreasing?
So low charge.
As you go from left to right, is electronegativity increasing or decreasing?
Increase.
And you need to understand why. As you go from left to right, same thing. My core charge is going to get a bit bigger because I have more protons. And that means that I'm going to be able to attract electrons more because I'm a much stronger atom now. So we're attracting electrons more because my core charge gets higher. Does that make sense?
Yeah.
Right. What about as you go from top to bottom?
Decreases.
Why?
Because there's more shells.
Good. And what does that mean?
That they get stuck to the shells.
Not that they get stuck to the shells, but it's like, all right. Imagine that. All right, imagine that I am the nucleus and you're an electron. Right now, you can come and touch me, right? But imagine that I was wearing like a big suit of armor with lots of layers. Could you touch me?
No.
You could just touch the armor, right?
Yeah.
So you can't actually get to me. Same thing. If there's more shells, those electrons are going to be further away. They can't actually come to the nucleus anymore because now there's like this layer between them. There's all these shells between them. And if I wear more and more armor, you're going to be further and further away from me, yeah? Imagine that I wore like 10 layers of armor right now. You probably couldn't even get near me in this room because I'd be so big. And so you can't actually come close to me anymore. Does that make sense? So it's like the less shells that they have, the smaller the atom is and the closer you can actually get to the atom.
Yeah.
Okay? All right. So what I'm going to do is just scroll down a little bit. So if you look at so what we're just discussing right now is the trends in the groups and in the periodic table. So this is what I'm looking at, right? Like electronegativity trends down a group, trends across a group, right? And so what I want you to do for homework is fill this out. So I want you to take your time and think about it. You have all the basics that you need. I've explained 2 things about atomic radius and things like that. So think about what the trends would be down a group. So would electronegativity increase or decrease? Would first ionization energy increase or decrease? Yada yada. And think about it. It's usually to do with core charge.
So
So
it's
just
just
think
2
about,
words, right?
yeah. So would it increase or would it decrease? But you actually need to think about it and actually get those right. For the oxidant strength and reductant strength, what I want you to do is I want you to just have a Google of those two and try to think about what they mean. It's really easy. I'm just not going to go through it because I'm giving you a lot of definitions today. But if you just Google them, it'll have a one-word explanation for what they are. Okay.
Yeah.
Long story short, oxidant strength is how likely it is to gain electrons, and then reductant strength is how likely it is to lose electrons. Same thing. Okay, cool. And just keep going down.
Oh, more.
Yeah, keep going down a little bit more. Yeah, all right, we'll stop there. Cool. And so remember the other thing that I said to you a little while back, that in chemistry now, one of the things that they're doing is that they're talking a lot about green chemistry. Have you heard of green chemistry before?
Yeah.
What is it?
I don't remember.
All right, so green chemistry is that we're just trying to do things that are good for the environment. So back in the day, we used to have lots of chemical reactions that would produce lots of nasty things, and they'd be very wasteful and things like that. But now all the chemical reactions that we're trying to do, we're trying to make them green. So we're trying to make sure that there's minimal waste and things like that. And so there are these things called green principles. And these are the main green principles that you need to know, right? So atom economy, catalysis, design for degradation, design for energy efficiency, designing safer chemicals, prevention of wastes, and use of renewable feedstocks. Okay, so what I want you to do is I want you to revise each of these terms because we went through them at the start. Okay, so write these down, Summer, so you don't forget to do it.
Can't remember.
Yeah, go for it. So revise green energy principles.
Chemistry. Oh wait, sorry. Green one.
Yep, the green chemistry principles. Sorry, yep. So that's those ones on that page right there. And then on the page above that, have a go at answering those questions about trends in the periodic table.
So above trend.
Answer questions above about trends in the periodic table. And so make sure that you have a go at all of these questions.
Yeah.
I know that the oxidant reduction strength, technically we haven't practiced it yet, but just, give it your best go. And then, don't worry about the rest of those questions, okay?
Yeah.
And then hopefully that should be the end of this booklet, okay? And then you really need to make sure that you put some effort into understanding what the atom is, what the atom looks like, okay? So I'll emphasize again and again and again and again. The middle is the nucleus. The middle of the atom has protons and neutrons in it, and it's surrounded by these shells of electrons. Okay, you need to understand that because you won't be able to understand anything else in terms of covalent bonding, metallic bonding, ionic bonding if you don't understand what the atom itself basically looks like. Yeah. So make sure you have a go at that work right there. All right. And the other thing that I want you to do for homework is just read this first page. Okay. So mainly, I want you to pay emphasis to this. What is covalent bonding? What is metallic bonding? What is ionic bonding? These are the 3 types of intramolecular bonds. So intramolecular bonds refers to how do atoms connect to each other. And there's only 3 ways. It's either through covalent bonding, metallic bonding or ionic bonding. So I want you to just read this first page and understand that, okay?
Yeah.
And then that way, if you understand this, then next week we can actually do these things really quickly, okay? So just write that down as well. I want you to read this first page of for week 3 covalent bonding and understand the 3 types of intramolecular bonds.
So can you say that again?
So read the first page of week 3 and understand the 3 types of intramolecular bonds. Okay. And right. And also just going to write something down. So and just really quickly write down here for each of them. So write down for covalent bonding, that covalent bonding occurs between non-metal atoms.
Yeah.
So yeah, just like draw a line and just annotate it and write down that covalent bonding occurs between non-metal atoms. So for example, carbon is a non-metal, nitrogen is non-metal.
Please can you say that again?
So it occurs between non-metals. Covalent bonding occurs between non-metals.
Non-metals.
Yeah. So things that aren't metal. So for example, is hydrogen a metal? Is
No.
nitrogen a metal?
No.
Is carbon a metal?
No.
So all of these things, if they were to bond with each other, they do covalent bonding. Metallic bonding occurs between metals, right? So just write that down. Metallic bonding occurs between metals. So it's when, for example, if I had to put iron and copper together, it would be through metallic bonding.
Between metals.
Yep. And then the last one, ionic bonding, is between a metal and a non-metal. So it's like if I had to put iron together with, I don't know, fluorine. So it's when I'm mixing a metal and a non-metal together, it occurs through ionic bonding, right? So just keep that in mind. So these are like the overall definitions, but then in simple terms, non-metals, metals, and then metal and non-metal, right? So it's the 3 different combinations that I can have because everything on the periodic table is either a metal or a non-metal. Just out of interest for you, I want you to know that everything here is a metal except for these guys.
Yeah.
Right? So these guys aren't metals. So boron, nitrogen, boron, carbon, nitrogen, oxygen, fluorine, silicon, phosphorus, sulfur, chlorine, arsenic, selenium, bromine, krypton. So it's not like this entire chunk. It's like this bit right here. So you start at boron and then you draw a diagonal this way. Right? So if I started at boron, I could just draw a diagonal this way. So it's like pretty much everything that's on this side is a non-metal. And everything over here is all metal. Yeah, so there's a lot of metals and not that many non-metals. Okay, so just keep that in mind. Yeah, make sure you have a go at all that homework before I come next week, and so that we can just get straight into it. Okay.
Yeah, I have a question.
Yeah.
Did you just assume genders? He said like these guys. He said these guys were.
Oh, I say that for
It could be girls too.
Could be, yes. All right. Whose photos are these?
Which mine.
Are they yours?
Yeah.
Oh, damn.
Grade 4.
All right. All good. Well, yes, in that case, I'll see you next Sunday, yeah?
Yeah.
Make sure you do that homework for me.
Yeah.
Don't forget.
Oh, my mom's not here today.
All right, all good. All good. No stress. I'll just let her know that I came back. Where's she at work?
Yeah.
Okay, cool. Just let her know that I was here.
Yeah. Thank you.
No worries. Right, I'll see you on Sunday.
Yeah. What's up, people? What's up, people? Why is my thing working? What an American boy. Hello? Hello? What the fuck? Hello? Hi. Hi. Why is my mic working? It's not turning green. Hi. Bro, can you hear me?